Okay, so I was speaking about eigenvalues and eigenvectors for a square matrix. And then I said for data, for many other applications, the matrices are not square. We need something that replaces eigenvalues and eigenvectors. And what they are is, and it's perfect, is singular values and singular vectors. So may I explain singular values and singular vectors? This slide shows a lot of them. The point is that there will be two, I don't say eigenvectors, two different left singular vectors. They'll go into this matrix U. Right singular vectors will go into V. It was the other case that was so special. When the matrix was symmetric, then the left eigenvectors are the same as the right ones. That's sort of sensible. But a general matrix, and certainly a rectangular matrix, we've got two sets of, well, we don't call them eigenvectors because that would be confusing. We call them singular vectors. And then in between are not eigenvalues, but singular values. So here's the, hiding over here is the key. A times the V's gives sigma times the U's. So that's the replacement for AX equal lambda x, which had x on both sides. And now we've got two, but the beauty is, now we've got two of those to work with. We can make all the U's orthogonal to each other, all the V's orthogonal to each other. We can do what only symmetric matrices could do for eigenvectors. We can do it now for all matrices, not even square. It's just this is where life is. Okay. And these numbers instead of the lambdas are called singular values, and we use the letter sigma for those. And here's a picture of the geometry in 2 by 2, if we had a 2 by 2 matrix. So you remember, factorization breaks up a matrix into separate small parts, each doing its own thing. So if I multiply by a vector x, the first thing that's going to hit it is V transpose. V transpose is an orthogonal matrix. Remember I said we can make these singular vectors perpendicular. That's what an orthogonal matrix. So it's just like a rotation that you see. So the V transpose is just turns the vector to get here, to get to the second one. Then I'm multiplying by the lambdas, but they're not lambdas now, they're sigmas. The matrix, so that's a capital sigma. So there's sigma 1 and sigma 2. What they do is stretch the circle. It's a diagonal matrix, so it doesn't turn things, but it stretches the circle to an ellipse because it gets the two different singular values in, sigma 1 and sigma 2. And then the last guy, the U is going to hit last. It takes the ellipse and turns it again. It's again a rotation. Rotation, stretch, rotation. I'll say it again. Rotation, stretch, rotation. That's what singular values and singular vectors do, the singular value decomposition. And it's got the best of all worlds here. It's got the rotations, the orthogonal matrices, and it's got the stretches, the diagonal matrices. Compared to those two, those are the greatest. Triangular matrices were good when we were young an hour ago. Now we are seeing the best. Okay, now let me just show you where they come from. So how to find these V's? Well, the answer is, if I'm looking for orthogonal vectors, the great idea is find a symmetric matrix and with those eigenvectors. So these V's that I want for A are actually the eigenvectors of this symmetric matrix A transpose times A. That's just nice. So we can find those singular vectors just as fast as we can find eigenvectors for a symmetric matrix. And we know they're, because the A transpose A is symmetric, we know the eigenvectors are perpendicular to each other, orthonormal. Okay. And now what about the other ones? Because remember we have two sets. The U's. Well, we just multiply by A and we've got the U's. Well, and divide by sigmas, because these vectors u's and v's are unit vectors, length 1. So we have to scale them properly. And this was a little key bit of algebra to check that not only the v's were orthogonal, but the u's are orthogonal. Yeah, it just comes out. So this singular value decomposition, which is maybe, well, say 100 years old, maybe a bit more, but it's really in the last 20, 30 years that singular values have become so important. This is the best factorization of them all, and that's not always reflected in linear algebra courses. So part of my goal today is to say, get to singular values. If you've done symmetric matrices and their eigenvalues, then you can do singular values. And I think that's absolutely worth doing. Okay, yeah, so, and remembering down here that capital sigma stands for the diagonal matrix of these positive numbers, sigma 1, sigma 2, down to sigma r. The rank, which came way back in the first slides, tells you how many there are. Good, good. So that's, oh, here's an example. So I took a small matrix, because I'm doing this by pencil and paper, and actually showing you the singular values. So there's my matrix, 2 by 2. Here are the u's. Do you see that those are orthogonal? 1, 3 against minus 3, 1. Take the dot product and you get 0. The v's are orthogonal. The sigma is diagonal. And then the pieces from that add back to the matrix. So it's broken my matrix into a couple of pieces, one for the first singular value and vector, and the other for the second singular value and vector. And that's what data science wants. Data science wants to know what's important in the matrix. Well, what's important is sigma 1, the big guy. Sigma 2, you see, well, it was 3 times smaller, 3/2 versus 1/2. So if I had a 100 by 100 matrix or 100 by 1,000, I'd have 100 singular values. And maybe the first 5 I'd keep. If I'm in the financial market, those guys, those first numbers are telling me maybe what bond prices are going to do over time. And it's a mixture of a few features, but not all 1,000 features, right? So this is singular value decomposition, picks out the important part of a data matrix, and you cannot ask for more than that. Here's what you do if the matrix is just totally enormous. Too big to multiply, too big to compute. Then you randomly sample it. Yeah, maybe the next slide even mentions that word randomized numerical linear algebra. So this, I'll go back to this. So the singular value decomposition, this is what we just talked about with the u's and the v's and the sigmas. Sigma 1 is the biggest. Sigma r is the smallest. So in data science, you very often keep just these first ones, maybe the first k, the k largest ones, and then you've got the matrix that has rank only k, because you're only working with k vectors, and it turns out that's the closest one to the big matrix A. So this singular values, among other things, is picking out, putting in order of importance the little pieces of the matrix, and then you can just pick a few pieces to work with. Yeah. And the idea of norms is how to measure the size of a matrix. Yeah, but I'll leave that for the future. And randomized linear algebra, I just want to mention. Seems a little crazy that by just randomly sampling a matrix, we could learn anything about it. But typically data is sort of organized. It's not just totally random stuff. So if we want to know, my friend in the Broad Institute was doing the ancient history of man, so data from thousands of years ago. So he had a giant matrix, a lot of data, too much data. And he said, how can we find the singular value decomposition, pick out the important thing? So you had to sample the data. Statistics is a beautiful, important subject, and it leans on linear algebra. Data science leans on linear algebra. You're seeing the tool. You know, calculus would be functions, would be continuous curves. Linear algebra is about vectors. It's just n components. And that's where you compute, and that's where you understand. Okay. Oh, this is maybe the last slide to just help orient you in the courses. So at MIT, 1806 is the linear algebra course, and maybe you know 1806 and also 1806 Scholar, SC, on OpenCourseWare. And then this is the new course with the new book, 18065. So its number is sort of indicating a second course in linear algebra. That's what I'm actually teaching now, Monday, Wednesday, Friday. And so that starts with linear algebra, but it's mostly about deep learning, learning from data. So you need statistics, you need optimization, minimizing big functions. Calculus comes into it. So that's a lot of fun to teach and to learn. And of course, it's tremendously important in industry now. And Google and Facebook and so many companies need people who understand this. And and then I'm repeating 1806 because there is this new book coming, I hope. Did some more this morning. Linear Algebra for Everyone. So I have optimistically put 2021, and you're the first people to know about it. So these are the websites for the two that we have. That's the website for the linear algebra book, math.mit.edu, and this is the website for the Learning from Data book. So you see there the table of contents and solutions to problems, lots of things. Thanks for listening to, this is what, maybe 4 or 5 pieces in this 2020 vision to update the videos that have been watched so much on OpenCourseWare. Thank you.